So, unprojected data, geographic coordinate systems are unprojected, stored in degrees, minutes, and seconds. And here again, I've given you the values a couple of different times. But when you're dealing with unprojected data, it's good to remember what those values actually mean: degrees, minutes, and seconds. And I've given you the English equivalents. And here we've got both the metric and English equivalents, where a degree is 110 kilometers or 69 miles. 0.001 degrees equals 110 meters. 1 minute equals 1.15 miles. 0.0000001 degrees equals zero point 0.1 meters. 1 second equals 104 feet. These are measured at the equator. They vary a little bit as you move away from the equator towards the north and south poles, but we're not going to worry about the nuances of that in this class. You may come up to where you need to deal with them in projects out there in the real world, but for the most part, um, these general measurements work pretty well for estimating distances between degrees, minutes, and seconds. And we'll just leave it at that in this class. So we've got the degrees, minutes, and seconds system in place. And now we need to start dealing with what's the actual geometry of the planet. And it is not a true sphere. We cannot use a geometrical true sphere to describe the actual shape of our planet because it's spinning on its axis. That spin imparts a force and it flattens the planet north and south a little bit, squishes it, and it squishes out east and west. So the equatorial diameter is a little bit larger than the polar diameter. And there we have a major and minor axis, is what we will call those things in cartography. The major axis being along the equator, the minor axis being along the north south between the poles. And the major axis is longer, the minor axis is shorter. The flattening as a ratio is about 1/298th, so it doesn't seem like all that much, but when you think about it at the size of the planet, a 1/298th flattening, it makes it no longer spherical at all. So it's something that we call an ellipsoid. Not a true circle, but it is, or not a true sphere, but it is semi-spherical. And that influences how we have to worry about transforming the 3D surface into a two-dimensional surface. After the ellipsoid, which is a mathematical representation of the surface, okay, now we start thinking about, well, what's it really like? So that mathematical representation is fairly perfect as an ellipsoid. We could draw a perfect ellipsoid, but we do have a more of a roughness to the Earth's surface, and that is controlled in part by the differences in elevation and in part by gravity. Okay, so the actual terrain surface is something we call the geoid. Okay, and that's influenced by gravity measurements. Some parts of the planet have um, higher gravity values than others, depending upon what kinds of minerals and rocks are beneath the surface in different locations and whether it's a water body or not. So the Earth's surface, in actuality, if you looked at it at scale, is fairly rough, and it's not going to be geometrically perfect. And so it's hard to come up with a one mathematical model that fits every single point on the Earth's surface at the same time. So we wind up needing to create several different levels or scales of mathematical representations of the planet's surface based upon our measurements from surveying, using old style surveying equipment, based upon surveys that we've done from the space shuttle, from the International Space Station, other satellites, and gravity measurements. Okay, so we have very complex surfaces. We do use the ellipsoid to generalize that surface, And let's move on to the next slide where we start putting things together. Okay, and so we've got the mathematical representation of the planet, not as a sphere, but as an ellipsoid. We've got gravity measurements, so we know something about how the Earth's surface bulges and how it sets back a little bit from a sphere. And that we can pull together in something we call a datum. And the datum is being used, it uses both our mathematical estimate of what the Earth's surface is and our measurements from these days gravity based instruments on satellites. And so we get here a mathematical fit between the measurements and the ideal, and we call that a datum. And the closer we can make those measurements fit what's actually on the Earth's surface, the better the datum is. We can create datums at the global scale, and those are used for the entire planet all at once, but they may not be very well fitted to local variation in gravity or local variation in terrain. And so some of the larger regions of the planet that have very good science programs in different countries have developed more local or regional datums that do a better job of describing what the Earth's surface is like there. And that local datum may be far better at describing that particular area than the global data set does. So you have a choice when you're dealing with different data sets and start thinking about coordinate systems to use. Which one is going to be the better one for what I want to do? If you're dealing with a global data set, then a global based datum is probably going to be your best choice. If you're looking at working primarily on one continent or another, you may prefer to use a datum developed for that continent or a datum developed for a portion of that continent. There may be, for example, different datums that could be designed to work for Canada, maybe one for Mexico here in North America. So you may be able to get even a better fit of the real world geometry. So then our data sets based upon that geometry are more accurate and precise. And this particular text image is coming from a different textbook. And it's kind of pulling together everything that we've been talking about for the last little while. The Earth's surface is not perfectly symmetrical. It's irregular. We use a mathematical reference ellipsoid to describe it. We know that the Earth's surface is actually more complex than that ellipsoid, and that's where we get this geoid idea from, measuring the actual undulations of the Earth's surface using gravity measurements. And so we try to do as good a job as we can of describing what that Earth's surface looks like as a mathematical model by combining these different measurements and estimations of the Earth's surface. And I'll just tell you right up front, none of them are perfect. None of the datums are perfect. But some are better suited for some areas. If you're looking at the whole planet all at once, again, a global datum is best for that. If you're looking at some smaller portion of the Earth's surface, if you can find a datum and projections that are based on that datum for that region or for that locality, then those are going to be more accurate. And it's just that they're able to be more accurate because they're dealing with a smaller piece of the Earth's surface. They're better able to model the Earth's surface within the computer. So datums then are the combination of this idea of an ideal sphere, which we know doesn't exist on our planet. Anyway, our planet is not one. It's more of a spheroid, more of an ellipsoid. We take gravity measurements or surveying measurements of the Earth's surface and the undulations and dips and valleys and peaks and mountains on the surface. We have a mathematical representation of that combine that with the ellipsoid or the spheroid, and then adjust. The adjustment of fit on the slide is referring to where we put the center of the planet. And so the center of the planet will not be in the mathematical center of the spheroid. It's going to be in the mathematical center of the geoid. But we take the coordinates from the spheroid, add them to the geoid, and together then these are what we call, and what ArcGIS in particular calls, a geographic coordinate system, or geographic coordinates. So that's something to remember about the workbook when you're working through the exercises. You may see Price, the author, using this acronym GCS, or Geographic Coordinate System, or Geographic Coordinates, and those are all pretty much meaning the same thing. What you're seeing here, the 3D reality of the globe, is defined by the datum, which is then a geographic coordinate system, usually measured in degrees, minutes, and seconds. In North America, we have several different datums that are used that are better for the continent. North American datum 1927, which can be contracted to NAD 1927 more commonly. We just call it NAD 27. As we say here in the notes, it's based upon the Clark 1866 spheroid. It was commonly in use until the 1980s, and you still find it used on some data sets these days. So if you think about this one, 1866, that's before satellite technology existed. So what we're looking at is something that incorporates more manual surveying techniques on the Earth's surface being incorporated into that mathematical model of the datum. North American datum of 1983, NAD 83. This is more commonly used today. And if you get a data set and you're not sure what it's in, this is what you should probably guess that it was built in, is NAD 83. This one is incorporating more satellite image measurements, or not satellite image necessarily, but satellite-based measurements of gravity. Another one that's used out there, and it's one that I come across only infrequently, but it exists, is the North American datum 1983 for the HARN network, High Accuracy Regional Network. And so this one is more accurate, perhaps, in some ways than NAD 83, but it's not very well adopted. And I haven't seen a lot in the literature as to why that's the case. But it is a data set that exists out there. It's one you may run into when you bring in information from other sources. Anyhow, and another one that we commonly use for geographic data is the World Geodetic Survey, WGS 84, which is a worldwide datum. And for most GPS, handheld GPS units, this seems to be the default datum that is used for them, but you can't count on that. Here's where I should probably make a point about doing field work with a GPS and which datum and or projection you're using. When you're given a GPS unit to take field measurements as a student or as a worker, it's your job to make sure that thing is set properly, and you need to understand what you're taking your point locations in. Is it in just straight WGS 84 geographic coordinates, or is it actually taking coordinates down in NAD 83, which is based upon a different set of characteristics of the Earth's surface? Those are actually going to give you different locations on the Earth's surface if you put them in the wrong datum. Okay, so this is something that's very critical. I have problems with this every year with students that come from other departments. In summer they did work and they took points and they have no idea what datum their unit was set to, and they can't get it back because someone else is using it now and all that jazz. So if you're doing field work of some kind, it's your job to write down somewhere, make a note, what the settings of the GPS are. Write down all of the settings that it's using to record your point locations. And it's going to save you a lot of heartache down the road. So projections now, we're starting to filter away from straight geographic coordinates into projecting our data. Every projection that exists, and again, there are thousands and thousands and thousands of these, is going to be based on some geographic coordinate system, some datum. Okay. So every projection then, therefore, has a datum. And if they're not matched, your geographic data that you have in these data sets may not match each other. And they can be offset from one another, as we see here, using examples of an air photo taken in NAD 27 and a road network in vector shown in NAD 83. They're both in the same projection, Universal Transverse Mercator, Zone 13, but they have different datums. So they don't match. Now, if you look closely, you can see where the roadway should be projected to match the image that's underneath it, but it's off. It's off by quite a bit. In fact, it's off by so much that you cannot, in any good conscience or any defensible way, do analysis using these two different data sets. They just don't match each other. They're not nearly close enough. Okay, so you're going to have to do something if you have data that's this far off, where you can visually detect it. I don't even have to do any math on this. I can just visually detect these are not right. So the simplest thing to do would be to reproject one data set or the other to match the other one. In this case, it's just a datum transformation, which is very simple to do in ArcGIS. But unless I do that, my analysis, whatever I'm doing with this, is not going to be correct. So watch out for those. You want to match projections as much as possible. And the best practice is to select a projection for the project and use that projection for every data set that you bring in. And so if you're bringing in new data sets that are not in your project target data geographic coordinate system, your projection, then you need to transform it into that proper projection at the beginning. Before you do any of the other analysis, you need to match those projections and then go forward for all data sets that you bring into any given project. So here, again, I've already made this claim on another slide, but we'll do it again. Your GPS unit may have the capability of recording in more than one datum or more than one measurement system. So it's up to you, the user, to make sure that you're recording information in what you expect your information to be stored in. So you have to know the settings. So get into the settings, figure out what they are, understand when you are recording point locations, or if you're taking point locations off the screen and writing them down on a piece of paper, you need to know what datum that information is being measured in and if it's projected or not. Some GPS units will record point locations in projections. So you need to know what that is. And if you don't, when it comes time to transform your field data into point locations to use in analysis, if you come to me or someone else and say, you know, I took these points with a GPS, but I don't know what to do with it. First thing we're going to ask you is, well, what datum and projection were you using? What coordinate system was it? And if you don't know, then we just say, well, congratulations. You have information that really can't be used for anything. It wasn't recorded properly. And any decent scientist is not going to touch that information with anything. We're not going to go there. So it's imperative that you, as a GPS user, know your unit, know how it works, know what it's recording information in, and be diligent about that.